So today we are going to look at these questions. So this is the final examination questions for semester 2, 24 and 25. Okay, so we are going to solve these first questions. So first of all, we have to state what is Gauss law. Okay, so here we have to define what is Gauss law. Okay, so you can state it. Okay, so the Gauss law says that the total flux that come out from a closed surface is equal to the total charge enclosed by the surface. Okay, so you have to explain the definitions of the Gauss law. Okay, so using sentences, then you can write down the formula. Okay, for the Gauss law, that is the total, if we integrate. Okay, so the total flux coming out from the surface, okay, we will be getting the total charge that is enclosed by the surface. For question B, so we have a positive charge, okay, is placed at the center of a solid conducting sphere with radius A, and assume the charge is distributed uniformly. Okay, so we have to find the electric field everywhere. So let's draw this situation. So you have the charge. Okay, so assume that the charge is a positive charge. Okay, and then you put it, okay, at the center of a conducting sphere. Okay, so this is a solid conducting sphere. Alright, okay, and this solid conducting sphere doesn't contain any charge. It's just a solid, okay, conductor, okay, no charge, okay, on this sphere. So we have to find the electric field everywhere. Everywhere means that we have to find the electric field, okay, when the R, okay, is less than the radius of the conducting sphere. Okay, so the conducting sphere has the radius of R. Okay, so we have to find the electric field, okay, in the region whereby I would say that this is A. So the A is smaller than the R, and also we have to find the electric field, okay, electric field that is outside, okay, outside this conducting sphere. Okay, I would say that this is A greater than R. Okay, greater than R. Okay, so let's look at the first one when the R is less than when the A is less than the R. Okay, so for the case A less than the R. So for the area A less than the R, it is inside this conducting sphere. Okay, inside, okay, conducting sphere. Okay, so we all know that there is no electric field inside a conducting sphere. Okay, so this is a very important property. Okay, so no electric field inside conducting sphere or conductor. Okay, I would say that conductor. Okay, so when there is no electric field inside the conductor, it also means that, okay, the electric field, okay, in the region A less than the R is equals to 0. Okay, so no electric field in the conductor. Okay, so we look at the second case whereby the A is greater than the R. Okay, greater than the R. So means this second region, okay, this one, A greater than R. So if we apply Gauss law, it says that the total flux, okay, that is coming out from the Gaussian surface is equal to the total charge that is enclosed by the surface. Okay, so you can see this Gaussian surface, the red color one, okay, this one, okay, this is enclosing one charge, okay, which is the positive charge at the center. Okay, so over here we'll refer to the positive charge, okay, at the center, and over here will be the flux that is coming out, okay, from the Gaussian surface. So you have a positive charge here, so the electric field, okay, will go to this direction, right? Okay, go to these directions, radial directions, okay, R directions. So we use the usual way, okay, for us to define the flux that is in the R directions. Then we dot product with the ds, okay, for the ds, so it is R sine theta, okay, d theta and d phi. Right, this is usually what we do, okay, you can refer to our notes. This is how we define the dx that has the directions, so over q here. So d theta is the range will be from 0 to pi, phi will be 0 to 2 pi. Right, so if you're pressing your calculator, okay, over here you will get 4 pi d, oh, here is r square, right, dr square, right, and equals to q. Okay, so this derivation is the same like we do the derivation when we have a point charge. Okay, so you can refer to that. So our d will become q, okay, over 4 pi r square, okay, and our e, okay, because the d is equal to epsilon e, okay, so it will be equals to q over 4 pi epsilon naught, okay, and r square. So this is our electric field in the region r greater a greater than the r, okay, and is in the r directions. All right. Okay, we look at the second question. So based on the answer in question 1b1, you have to sketch the graph E versus the R. Okay, so the R over here is actually representing the distance. Okay, distance. So the electric field is actually a function of distance, right? Because if you look at the equations, okay, this electric field equation is a function that has the R. So they are asking you to plot a graph, okay, that the E, okay, versus the distance R. Okay, so basically we have two regions, right? When the A is less than the R, and when the A is greater than the R. Okay, so two regions that have different electric field. So for the region R, A less than the R, okay, so the E is equal to 0. Okay, whereas for the A greater than the R, the E is represented by these equations. Okay, so when it comes to plotting, okay, so we can put a graph here. Okay, so this is our electric field and this is our R. So over here, I will mark it as A because when A is a transition point, okay, to have a different electric field. So in between 0 to A, right, so the electric field is 0. Electric field is 0. And for the A, right, for the A, you start to have some values, right? So this is the equation. So we only look at the equations. We don't look at the direction. So the equation is Q over 4 pi epsilon naught. Okay, I purposely separate this R square. Okay, so this one, yeah, we don't know the value, but we can treat it as a constant K. Okay, so if you have no idea about the shape over here, whether it is dropping straight or dropping exponentially or going up, okay, if you are not sure how to do this, okay, you can construct a simple table. Okay, so over here you have the value of A, the value of R, sorry. Okay, over here you will have the value of R, and over here you will have the value of E. Okay, so what will happen if the R is equals to the A? Okay, so it will be 1 over A squared, right? So over here I will say that the K is 1 over A squared. A squared. Okay, 1 over A squared. And let's say I give a value for the A. Okay, I give a value for the A because I need values for me to block the graph. Okay, so if I say that the A is equals to 1, okay, so what will happen here? Okay, so here will become 1 over 1, okay, which is equals to 1. Okay, so over here you have the K. And if the R is 2, okay, you will have 1 over 4. Okay, so you can see that the value is dropping, okay, from 1 to 0.25K, okay, dropping, and 3, okay, 1 over 9, okay, the value is dropping again. Okay, the value is dropping again. So you can see the value is dropping. So over here, we know that it is dropping like this. Okay, it's dropping like this. Okay, it's not a straight line, but a curve. Because you see that the it's not making a straight line. Okay, so we draw a curve over here. Okay, so here we are going to put a straight line over here. Okay, so this is the transition point. And you have a value here. Okay, so it depends on the value of this K. Okay, depends on the value of the K. Right, so this one would be your graph. Okay, it will be your graph. Alright, let's look at question number 3. So based on the answer, okay, in the second question, describe. Okay, describe means that you have to explain the behavior of the electric field in sentences. Okay, so this is the graph that we draw just now. So now we are going to describe this graph, okay, in sentence. Okay, so you can say that, okay, the electric field. So the electric field, okay, when the A is less than the R is equals to 0. Okay, so just mention equals to 0. And when the A is greater than R, okay, the electric field intensity, okay, reduce, okay, with the ratio of 1 over R squared. Okay, so this is how the electric field intensity drop versus the distance. Okay, so just mention it in sentence, yeah? Okay, now let's look at question C. So the space between two spherical conducting shell, okay, at the R 5 cm and 10 cm is filled with a dielectric material. Okay, so this is the property of the dielectric material in between terms, and the two shells are maintained at a potential difference of 80 volt. Okay, so the first question is we must shows that, okay, the capacitance of the capacitors is this one. Okay, so this is about derivations. Okay, derivations. Well, you have to derive the equations, okay, for the capacitance or spherical capacitors. Okay, so this is the case. Okay, so you have an outer shell and you have an inner shell. Okay, so remember what the question say. Okay, so you have two radius, right? So for the inner radius, okay, it is 5 cm. Okay, but here we use alphabet to represent it because we need to derive the equation for capacitance. And this one is the radius of outer spherical shell, and in between terms, okay, they are filled out with dielectric. Okay, dielectric. So the dielectric is equals to 2.25. okay, of epsilon naught. Okay, so we can represent the dielectric using this symbol. Okay, so to come up with the equations, so the first thing appear in your mind should be these equations. So this is the general equation for capacitors, no matter it is parallel plate or coaxial or spherical. Okay, we are using this one. So our task is to find this V and then put the V into this equation to get the capacitance equations. So in order to get this one, we need to find out what is the E, right? Because the V is equals to integrate E dl. Okay, and this E, we can get it from the Gauss law. Okay, the Gauss law says that the total flux that is coming out from a Gaussian surface is equal to the total charge that is enclosed by the surface. Okay, so this is the thing. So we can get the E from the D, because the the D is equals to epsilon E. Okay, so this is how we progress, okay, to the capacitance equation. So the first thing would be applying the Gauss law. Okay, so we have to apply the Gauss law. So the Gauss law says that the total flux that is coming out from the Gaussian surface will be equal to the total charge that is enclosed by the Gaussian surface. So look at this case. Okay, so by assuming that, okay, the inner conductor is connected to the positive terminal of a voltage source, and then the outer conductor is connected, okay, to the negative terminal, okay, of a DC source. Okay, right? So the electric field will be going out this way, right? Going out this way. So if you want to find the electric field in between inner conductor and outer conductor, which means that if you want to find the electric field in this region, okay, right, this region, so I will draw a red circle to represent that this is the Gaussian surface. Okay, so for the Gaussian surface, okay, so we can use this formula. So the D, okay, is in the R directions, okay, and then we have R square, sine theta, d theta, and d phi. This is what we always do, right? And this is equals to Q. Say that it is equals to Q, right? So over here, don't miss out this R. Okay, it is equals to Q. So the theta is 0 to pi. The phi is 0 to 2 pi. Okay, so over here, you will usually get d R square 4 pi, right? And over here, it will be Q. Okay, so the E will be equals to Q over 4 pi R square, and then you have an epsilon, right? Okay, so this is the E, and in the R directions. Okay, so now we are going to replace the E in the equations for the potentials. So the potential is equals to negative integrate E dot dl. Okay, so here will be negative, so I will be integrating, okay, from the positive terminal to negative terminal. So I will be integrating from A to B. So I will put in my equations for the electric field. Okay, just put it in, and then you have the direction. And for the dl, okay, is replaced by the dr, because the L stands for the length, the distance, okay, the distance in between, okay, A and also the B, okay, A and also the B, right? So it is in R directions, okay? So we do the integrations. So I will take out this 4 pi epsilon, okay? So I will focus just this 1 over R square dr. Right. Okay, so when you integrate, this become R negative 1 over negative 1. Right, and then B is here, A is here. Okay, so you have a negative. Okay, so this one will be Okay, so it will be 1 over b. So the negative, I decide to cancel it. 1 over b minus 1 over a. Okay, so after I cancel, I don't have this one anymore. Okay, so this one would be my v. Okay, so now I'm going to bring in this v into these equations. Okay, so q I have to divide with the v. Okay, so here it would be 1 over b minus 1 over a over the 4 pi epsilon. So you can cancel this. So eventually your equations for the capacitance will be this 1 over b minus 1 over a. Okay, so this will be your equations, okay, for the capacitance. Okay, don't worry about the positions of these 1 over b and 1 over a. In fact, they are the same thing because the capacitance cannot be negative value. So it is fine if you rewrite it to be 1 over a minus 1 over b in order to get a positive value. Okay, so the following question is asking you to calculate the capacitance. Okay, so by using these equations, eventually if you cannot derive these equations, right, in question number 4, you still can use these equations to calculate your capacitance. Okay, so what you need is this question number 4. What you need is the value of A and B, right? So the capacitance will be 4 pi. Okay, so for the epsilon, you are going to replace it with this, right? Okay, and 1 over A. A, according to the questions, the A is 5 cm. Okay, 5 cm. So 5 cm. So make sure that you convert it into meter. Minus 10 cm. Okay, make sure you convert it to the meter. Okay, so you can calculate the answer. Okay, your answer should be 0.025 nanofarad. Okay, so this one will be your answer. Okay, now let's look at the following question. Find the total charge, okay, on each shell. Okay, find the total charge on each shell. So meaning that we have to find the Q. Okay, so to find the Q, okay, we can manipulate these equations. C equals to Q over V. Okay, so C we already know it, right? So it is 0.025 nanofarad. So the Q would be C multiplied with the V. Okay, so it's 0.025 nanofarad. Okay, multiply with the V stands for the voltage. Okay, so question says that the voltage is 80. Okay, so you are going to get the answer 2 nanocoulombs. Okay, next we're going to look at this exercise. Okay, find the charge density. Okay, find the D. No, charge density is not this one. Find this one. Okay, surface charge density. Okay, at a distance R equals to 5 cm. Okay, R equals to 5 cm. So this, okay, charge density, we could relate it with the equations of this. Okay, if you want to know the total charge, okay, that is on the surface, you need to integrate the surface charge density with its area. Okay, meaning that this is going to multiply with the area. Okay, so now it says that, okay, the R is 5 cm, so it's 0.05. Okay, so we can find the area, okay, by using these equations. Okay, so 0.05 multiply with pi multiply with 0.05 square. Okay, wait, there is a mistake on the equation. It should be 4. Okay, 4. So let's calculate this one. Okay, so 4 pi Okay, let's calculate the answer. Okay, is equals to 4. Is it equals to 4? Let me check. No, okay, it's equals to 0.03142. Okay, 0.03142. Okay, so you are going to calculate this one, right? So it's Q over A. Okay, so you use the 2 nano coulombs. Okay, 2 nano over the 0.03142. Okay, so 2 nano 0.03142. Okay, so it's equals to 6.37 negative 8. 6.37 negative 8. Okay, 6.37 times 10 negative 8. Negative 8. Okay, coulombs.